Hello, my name is Fatima Masim and I will be presenting the final project I did back in 2021 during my master's course at Imperial College in Sustainable Energy Futures. My project consists of the life cycle analysis of storage batteries for PV water pumping systems in sub-Saharan remote areas. Water scarcity in Africa is still an important concern, and still 2.2 billion people are lacking safe drinking water. As it can be appreciated from the picture, most of the people who suffer from water access are located in the African continent. PV water pumping systems have proven to be an interesting solution from both an economical and technical point of view to provide water access to these remote communities. PV water pumping systems consist of 5 key elements: PV panels, a controller, a motor pump, pipes, and a fountain. Additionally, these systems normally include a storage technology to allow water access at any time. We can find 2 different architectures: a water tank, where the energy is stored in the form of water, and a battery bank, where the energy is stored in the form of electrochemical energy. This PV water pumping system was installed in Gogma in 2017 and has been used as a case study for this thesis. Gogma is a village of 250 inhabitants located in the center-east of Burkina Faso. In previous techno-economic studies, it was found that the life cycle cost of the tank architecture is almost $7,000 cheaper compared to the life cycle cost of the battery architecture. This brings the possibility to decrease the cost of water in sub-Saharan Africa. But these batteries are characterized for the environmental impact, especially due to the toxicity and scarcity of some metals. Therefore, the aim of this thesis has been to quantify the environmental impact of the storage technologies and develop a methodology that would allow the integration of environmental indicators in future studies. This study started with a literature review to identify the research gap. The life cycle analysis, known as LCA, has been the selector approach, which is the most comprehensive method when quantifying the environmental impact of a product or a service. It continued with the definition of the criteria by selecting 4 different technologies and analyzing all potential scenarios from extraction of raw materials to disposal of the end-of-life product. A total of 24 scenarios were identified. These were then modeled in the LCA software CIMAPRO using the EcoInvent database. Finally, results were obtained and analyzed. The 24 scenarios were classified per storage technology, per location, and per end-of-life treatment. As it can be seen, there were 3 key geographies of focus: China, Europe, and Africa, and all the scenarios go from material extraction to disposal, what is known as cradle to grave. There were 2 scenarios for the steel water tank, 4 scenarios for the plastic water tank, and 9 scenarios for each of the battery technologies. The presented results in this slide show the best 6 scenarios, which were selected from the 3 endpoint categories: human health, ecosystem, and resources. The 5 analyzed midpoint categories are the ones shown in the vertical axis. These results are presented in percentages, and as it can be appreciated, lithium-ion batteries in green and yellow and the plastic water tank in dark blue are the scenarios with the lowest environmental impact, with 365 and 780 kg of CO2 equivalent, respectively. On the other hand, lead-acid batteries in light blue and red and the steel water tank in pink represent the solutions with the worst environmental impact, with almost 2,000 kg of CO2 equivalent each. To conclude, 2 functional units have been analyzed, and therefore 2 conclusions can be made. One for meeting Gogma water demand, where lithium-ion batteries and plastic water tanks present the best environmental solutions, as discussed in the previous slide. And another one per kilogram of storage technology, where in this case, both water tanks become the best environmental solutions. The viability of both architectures has also been analyzed. The downside for water tanks is that they could provoke sediments obstacles, and therefore poor water flow. And the downside for batteries is that they will need various replacements, 1 for lithium-ion and 4 for lead-acid. Regarding future developments, this could be accurate estimation of lithium-ion lifespan and keeping life cycle inventories up to date, especially for lithium-ion technologies. Thank you for taking your time to listen, and thank you to the organizers for setting up this workshop and giving more visibility to the work that is being carried out. Thank you.